All right, welcome everyone to the second tutorial by the Michigan Football Analytics Society on Python. So we have a ton of R tutorials on the YouTube channel. So if you type in mfans YouTube to Google, or I guess you're watching it on this channel anyways, you can see that there are 4 R tutorials that were recorded a couple months ago, kind of going over how to aggregate NFL data in R. And this one was the first Python tutorial that we did. And today we're going to be doing another Python tutorial. So be sure to check out the other videos if you haven't already. Additionally, you can type in TageSet GitHub, which is me, click on my GitHub, and you can come to NFL Tutorials 2022. A link will also be in the description for this. I feel like a real YouTuber when I say that, but you can click on the code here, and this has all the code that we're going to use today. So like the great thing about this is you could just open it in Colab and have all the code ready. And we're going to use Google Colab today to do this. Some people I know use the Anaconda Navigator, Jupyter Notebook, Jupyter Lab. That's great. I didn't want to go through the whole download process for how to do that. So instead, we have Google Colab available for us to use here. So let's jump into the tutorial. Again, we'll just search Google Colab or get to it how you get to it. And again, thank you for all the feedback, the messages that people have sent me about these tutorials. I put a lot of work into these, so it means a lot that when people are messaging me, and it makes me want to continue to do these. So let's start here. So the first thing we got to do is install our packages. Again, if you did this in the first tutorial, you're not going to have to install a lot of these packages. Some of these packages you might have used before, but we're going to be installing some packages here today. And then we're going to be building a model using Python. So people always ask me all the time, do you prefer R or Python? And I like both of them a lot. And I started with R. I've kind of transitioned a little bit more to Python in recent years. And that's because the modeling aspect of Python is really easy and it's really intuitive. And we're going to see why today, right? Like we're going to be working with a binary response variable. If an outcome was a 0 or a 1, and we're going to be able to see how easy it is to model this using a couple different models. So this tutorial is going to go over loading in the libraries, aggregating the data, feature engineering, and then making those models and getting predictions out of them, which I think is going to be really, really cool. I'm not going to explain the math behind why these models work. That's for people a lot smarter than me to explain, but I am going to explain how to do these models. So let's kick us off here with pip install NFL fast py. And so again, we're just gonna pip install all of these libraries that we're gonna use here today. The only one that I think you have to run every single time, sorry, it's not NFL fast py, it's NFL underscore data underscore py. It used to be called NFL fast py. The only one that I didn't install in the last tutorial that we're gonna have to install here is gonna be sklearn and XGBoost. But all these other ones you should have installed already. But if not, you can just run all these lines or whatever. For some reason, NFL data underscore py is something that I need to install every time I use Colab. I don't know exactly why, but all these other ones seem to save for the most part. So I'm going to comment these out for now. And again, if you want a simple way to comment, you do Command Shift. Oh wait, oops, I did it. Command uh then the slash question mark key or control slash question mark key. So that's how you comment. I'm only going to run that one. If you haven't installed these 5 packages or 6 packages already, be sure to do that as well. But if you have, then you don't have to worry about that. So you should be good from there. Then now we're going to import a lot of stuff here today. There's going to be a lot of specific things we have to import for our model building aspect of things. So NFL fast or NFL data underscore py is importing. So we're gonna do NFL underscore data py as just NFL. Let's just call it NFL, just keep it simple. Import pandas as PD, which is the industry standard. Import matplotlib dot pyplot as PLT. Import NumPy as NP, again, industry standard. Import Seaborn as SNS. Import. Okay, so here's where we're gonna do a lot of import things. Import sklearn.model underscore selection. And we can see it fills it in for us. That's how we know we're doing it right. Or from sklearn model import stratified shuffle split. So that's going to help us with our training and testing data later on. From sklearn dot linear model import logistic regression. So we're going to use that later on. That's going to be pretty cool. From sklearn dot ensemble import random forest classifier. I've been told I say forest a little bit weird, so ignore that. But and then from sklearn.metrics import Briere score loss. And actually, let me zoom in here. It's a little bit easier to see, hopefully, for you guys watching on YouTube. But again, if any of these pop up where they have a yellow line underneath them, like that, this is not a real package or real library, but you have to go up here and type pip, the exclamation point pip install, and then whatever it has that yellow line under it. So just be on the lookout for that. And then you'll see why we're installing all of these a little bit further down here. So from XGBoost, import XGB classifier, run all of these, and you're gonna load all of these in here. So we're good there. So now we can load in our play-by-play data, which is a really cool part of what the NFL underscore data underscore PY package has to offer. So we're going to do NFL dot import PVP data parentheses and then a bracket. Basically, we're making a list of seasons we want to load in. So if you wanted to load this all the way back to 2010, you could type out those years individually. You could make a sequence list or something like that. We only have 3 years, so we don't have to do that. But this is how we're going to load in our data to work with today. As that's loading in, let's type out some code here. So it'll say when each year is done. So we're gonna look at the first 5 rows of the data. And then we're also going to want to print the shape. Oops. We're also going to want to print the shape like kind of manipulating, and then we're going to want to do it after we manipulate it. So, okay, let's look at the data here before we jump into that. So we have, okay, play ID, game ID, home team, away team, week, all this really good information as we scroll across it here. But here's what I'm noticing. There's some plays where things aren't happening that relates to us, right? Like what we want to do is we want to predict the chance of a sack on a play based on a bunch of variables. And there's some things on here that where a sack can occur, like a kickoff. So what we need to do is we need to filter out just passing plays. So pass equals 1. And we need it to be where there's no play on the play, like if they were about to pass and it got blown dead. So how we do this? PVP bracket open parenthesis PVP pass equals 1 and PVP play type equals no play. So what that's going to do is that's going to give us all passing plays that resulted in no play. And then again, we can PVP underscore clean dot shape. So we're making a new data set here. So we can see that we had, wait, that's not right. Oh, sorry. Does not equal no play. So we can see we started with 149,000 rows of data, and now we're down to 64,000 rows from the past 3 seasons. So that's exactly what we wanted here. So we're going to be predicting how often or when sacks occur, basically. So let's see how often these sacks occur. So what we can do is we can create a count plot that will basically group by and summarize sack or no sack, and then show that plot for us. And this is called exploratory data analysis, EDA. So sacks haven't happened on 60,000 plays, and then the other 4,000 sacks happen. So we can get like a good feel for, all right, on 4,000 of the 64,000 plays we have in our data set. So around 6% of the time is when sacks occur. That's what we should be predicting on. When do sacks occur, though, is what we want to see. So what we're going to do is we're going to say, all right, on plays that just had a sack, let's filter it. So PVP clean, bracket, parentheses, PVP clean, sack equals 1. And then we're going to use our count plot again, and we're going to see which downs do sacks occur on. So this is all exploratory data analysis right now, EDA. So this is interesting. First downs, second downs, it goes a little bit less. Third down, there's a lot of sacks that happen. That makes sense. And then fourth down, since there's not many plays, sacks don't happen that often. Something that's really cool in the data is you can see the number of pass rushers a defense has. So again, based on our sacks data up there, we're going to do a count plot. X equals sacks, number of pass rushers, and then plt.show. Actually, I'll show. So if you don't do plt.show, it like does this little like weird text right here, which is fine. But like plt.show, I think is like the better way to do it. So cool. We can look at this. Okay. Most plays have 4 pass rushers. That makes sense. 5 pass rushers, 6 pass rushers. So that looks like something we probably want to put in our model as well. So with all that being said, we have our clean data set up here. And again, if you haven't like gotten all the code like right yet, the code is in the description. There's a link to the code to the GitHub that will open up a Google Colab for you in the description. So we have our clean data set. We've made some plots that are interesting. If we were to put together like an article on this, we would use some of these plots probably in this article. PvP clean. So let's feature engineer now, right? Let's see, when do we think sacks can occur? They could occur in obvious pass situations. What should we define as obvious pass situations? Let's define it as 3rd and 6 or more. So obvious pass equals, that needs 2 S's. And we're going to use this np.where function. So it's going to tell us, all right, in 3rd and 6 or plus, mark a 1 for when it's obvious pass situations, or if it's not 3rd and 6 plus, mark a 0. So PvP clean down equals 1 or equals 3, and PvP clean yards to go should be greater than equal to 6. And if both of those conditions are true, mark a 1. If not, mark a 0. This is very similar to our if-else statement that we used in the R tutorials, right? This is very similar to those statements. Run that. Don't worry about that message. Eventually, we're going to have to change what we do here, but for now, we're good. So let's set up our data frame to do this modeling stuff here, right? So what should we keep? We should keep game ID, play ID, because those are markers. We should keep season. We should probably keep the name of the quarterback, because that'll be interesting to check. Down, we want to keep, because that's going to be part of our model. Yards to go, we're going to want to keep, because that's going to be part of our model as well. Yard line 100, that's important to have. Game seconds remaining, that will probably be useful in our model. And then we want to get some information on the defense. Defenders in box, great variable to have in there. Number of pass rushers, another great variable to have in there. And then the chance of them passing, which is another model that was created by Ben Baldwin. Obvious pass, and then SAC. So we need that SAC variable. That's our most important variable here because it's what we're modeling. There's probably going to be some NAs here. So let's check that. Is.na.sum. So that'll sum up columns. So we have 307 instances where a down isn't listed. We have 886 instances where defenders in the box. 3,000 out of the 64,000 that we have here don't have number of pass rushers. So we want to filter all those out. So let's map that to a new data frame, pre_df dot drop NA. So this is the function where it will get rid of all our NAs. And then we can run that. And now they all have 0 NAs. So we're doing something right there. Let's check our new data frame, the first 5 rows to see what we have. So we have our game ID, our play ID, we have our quarterback, our down, yards to go, defenders in the box, number of pass rushes, the chance of them passing, whether it's an obvious pass situation or not, which we marked as a 1, which is pretty cool. And then whether or not it was a sack. So no sacks appear in this top 5 here, which is fine. But we're going to want to kind of use that sack variable and predict it. Remember, it happens 6.5% of the time in this data set. We want to see what we can do from a modeling standpoint to predict when sacks are going to happen and see which quarterbacks are avoiding sacks the best and which quarterbacks are taking sacks the most. So down is an interesting variable, right? Because if we were to build a model that treated the difference between first down, second down the same as the difference between third down and fourth down, we don't want that. It drops from first to second down. It jumps up from second to third down. So we want to treat down as a category. So we're going to say as type category. So df down equals df down as type category. So we can't have in the model game ID, play ID, name, that's stuff that we want to be agnostic. So we need to create a new data set called df no IDs, where we drop game ID, play ID, name, and season. And then we have to also we have to one hot encode our data frame here. So df no IDs, columns equal down. So down is our category variable in the data set. So we need to kind of use that, right? And so then I'll put this on a different row. We run that. And now we can see we have yards to go, yard line, all this stuff. We have a sack or not. And then we also have our 4 downs. So what this is doing, for those who aren't familiar with one hot encoding, what this is doing is it's taking our category and it's placing a 1 when it's first down in the down 1. It's placing a 1 in third down when it's down 3, but it places zeros in all the rest. And this is a popular technique that can help with modeling. Now we can get into the fun stuff here. We can do modeling, right? So first thing we want to do, we need to create our stratified shuffle split. So we want to do one split. We want to have our test data set at 25% of the data, and then our training data set at 75% of the data. And so what this is going to allow us to do is we're going to train on the train data set, train our models, and then we're going to test on our test data set and see how well it predicted it on data it's never seen before. Because what you don't want is you don't want your models to overfit. So we're going to do for train index and test index in SSS.split, which is what we call that above. We're going to take df no IDs and df no IDs sac. And and we're gonna say strat train set equals df no IDs dot iloc train index strat test set equals df no IDs dot iloc test index. So it basically what this did was it set this SSS put all these indexes right here. See how these rows are labeled with the index that R gave or that Python gave? It set specific indexes for it to kind of split it up. And why we put this df no ID sac here is we want an equal proportion of sacs in the train data set as we have in the test data set. So now we can make our 4 data sets that we're going to use. Our train data set, so strat train test set dot drop, and we don't want sac in this data set because we're going to be predicting sac. So this is our y train strat train set dot sac or bracket sac. That now we can create our test set strat test set dot drop columns equals sac. Y test equals strat test set sac. So look, when we kind of look at this, we have our X train. This contains 45,000 rows. We have our Y train, also 45,000 rows, but it's just if they had a sac or not. We have our X test data set, 15,000 rows. So that shows that what we're going to be testing on. So let's create a logistic regression model. So LR equals logistic regression. So that you can call it whatever. Let's just choose to call it LR. Let's fit it on X train to Y train. So based on all these features here, we're going to try to be predicting sac or no sac. And then we can run that. And we can see it trains. And so now we can create predictions off of that. So pd.dataframe lr.predict underscore probability on our test data set. So X test columns equal. So first it's going to be no sac and then it's going to be sac. You can check this if you want just to make sure. That's just the order that it gets put in. So LR pred. So let's take a look here and see what we got. So we have the chance of no sac on the first play in our data set at 93%, the chance of a sac at 6.5%. This one's a little more interesting. There's a 11.9% chance of a sac happening here. So let's use a Briere score. So to test to see if this works, right? So here's the formula for Briere score that it uses. So 1 divided by n, where n is the number of data points, the sum of the prediction minus the actual value squared, and then you multiply it, right? So Briere score is a good test for if this outcome or not happen. Here's an example, right? So it did happen. It predicted a 1% chance of that happening. You square that. It did happen. It predicted a 99% chance of it happening. So our lower Briere score is really good, right? We only see that it had a 0.0002 Briere score here. So it did a good job. So this is good for a data set like ours that's zero inflated. We don't just want to test accuracy, whether or not it predicted, a greater than 50% chance. A Briere score is a really good way to see how off our predictions are, to see if we have a good model. So print. Let's just put some text here so we know it's a Briere score. And we're going to use Briere score loss. Remember, we loaded this in up there on our Y test and our LR pred. So again, this LR pred was on the test data. We're going to print. And I messed up. Y test, LR pred. Oh, my bad, my bad. I forgot. We just want to take the prediction of a sack here. So do double brackets at the end and then sack. Boom. Briere score of 0.058. That doesn't mean anything to us right now, but as we build our next model here, it will mean to us. So let's build a random forest model. So how does a random forest work? So it builds a bunch of decision trees. It could be 100 decision trees. It could be 1,000. And it says, all right, based on these decision trees, based on what we know about the data, can we predict these classes? And then can we give an overlying prediction? So let's say it built 100 decision trees and 5 of them predicted sack and 95 of them predicted no sack. So what the random forest is going to do is it's going to say there's a 5% chance of a sack happening on that play. It's a really cool modeling technique. There's a lot of math behind it that I'm not going to be able to explain. There's a really good YouTube channel called StatQuest, or if you Google StatQuest random forest, there's a lot of good videos here to watch. So if you want to get deep into the weeds behind that, please go ahead and do that. So we're going to use random forest classifier. rf.fit xtrain ytrain again. So that's going to be our training data. And then we got to create our pred, which is going to be the exact same code above. So this is why I love Python so much for modeling, is because it's all the same structure. In R, all the different modeling techniques were different. On Python, we can just do this. We can write the exact same code. I could even gone up and copy and pasted the code and just changed the model name, but I don't necessarily want to do that. So this is why again, Python is so good for modeling. R is good for so many other things as well, but Python is so good for modeling. So it's training our random forest here, and then it's going to print its Briere score. It's going to take a couple seconds. So this is really interesting. A lower Briere score is better, 0.059, 0.062. So the random forest did worse. Is that because it overtrained on the train data set and didn't do as well in the test data set? Possibly, but we don't know exactly why it did that, but it did do that. So that's interesting. Now we can go to XGBoost, which is my personal favorite. I'm not sponsored by them, but I like them a lot. So XGB classifier. And what do we have to do here? So first we have to set its objective. So we have to say, all right, so it's a binary logistic model. So there's a 0 or a 1 outcome. Let's set a random state. We'll do my favorite number, 42. And that's all we need. There's a lot of other things that you can set in here, right? Just hover over XGB classifier. Max depth is how far the trees will go. Learning rate, N estimators, verbosity, gamma. There's so many things you can do with this. And if I'll show you in a second how to like kind of mess with those. But for now, let's just keep the trained weights that it is. So what is the XGBoost classifier? Again, we're going to use Google here. So now we have a data set that's changing, or trees that are changing based on updating and going back in the data set over and over and over. So it's random forest on steroids, basically. It's really cool. So xtrain, ytrain. So we're going to do that again. And again, it's literally the same exact structure as what we did above. To save on time, let's just copy that. So again, be careful with copying code. XGB pred, XGB, we called that up here. We can literally do that again. And then Briere score loss, Y test, and then XGB pred. Oh. Let's see what I did wrong here. One second. Sorry about this. Let me check my pre-written code already to see what I did wrong here. Okay, maybe I just had a spelling mistake or something. Oh, sorry. I actually boost model already trained, and it has a better Briere score, barely, than the logistic regression. So let's roll with that again. So if you want to tune your XGBoost model, come to my GitHub, come to Hackasack, and go to build.py. And it has all this code here for how to tune it for the gamma, for the learning rate, the max step, the end estimators. It'll create a randomized search grid for you. We're not going to do that today because it'll take forever to train, and I want this video to be, relatively short. But that's how you can do that. There's other ways. You can just Google tune XGBoost model. So let's use our XGBoost model to make some predictions here, right? So so let's do this. Let's use this to make predictions. So let me just get my notes up here. So first we want to see the feature importance for this model. What features are making this make their predictions? How did we do so well with the XGBoost model? So XGB dot feature importance for arg sort. So what did this just do? That just sorted the features in a row for how we can get this. Then we can use xgboost.train.columns sorted IDX, and then XGB dot feature importances sorted IDX. And then let's show our plot here. So this will show us the feature importance. Third down is a very important variable for predicting whether or not a sack. That makes sense. The most sacks happen on third down. Look at our obvious pass variable that we featured engineered getting up here. Expected pass number of pass rushers. That makes sense. So all these things make sense for why our model's giving us our predictions, because it is a little bit of a black box, but it makes sense. So now we can make predictions off of what we just did. So make sacks preds. So we're going to take our df underscore no underscore IDs dot drop. We're going to drop sack, and we're going to do that on axis equals 1. Axis equals 0 would be on a row level. Axis equals 1 is on the column level. XGB total predictions equals PD dot data frame. And we're going to do what we did above, where we do predict proba make sacks preds. Column equals no sack, column equals sack pred. And we just want to keep sack pred. So that's our sack prediction. That's our likelihood of a sack occurring. So this is our sack prediction on each play, basically. Pretty cool. Sack preds equal. So we need to reset our index above, because this starts with an index of 0, but above it was taken from a data set where some plays were filtered out. So reset our index, and then we also need to drop. It'll create a column called index. So we need to drop that. And then let's map this data set, XGB total predictions, as a column in Sachs Preds and see what that looks like. So now we have the percent chance on each play that a sack will occur based on all this game state or whatever. So now let's see which quarterbacks do the best job of avoiding sacks. So we need to create a new column called sacks over expected. So basically, what's your probability of a sack? And then did you actually take a sack or not on that play? Now, it is a little bit dangerous to assign the total blame to the quarterback. We don't have offensive line data to work with here. So quarterbacks with bad offensive lines might show up poorly or something like that. But and you also, in an over expected model, you don't want to assign the total model error, the residual, to the quarterback. But this is just in case you wanted to do something like this. You can do that. So we're going to group by name. We're going to filter on season equals 2022. We're going to group by name, and we're going to do .ag sack. So we're going to just count straight up. How many sacks did you have? Then let's count straight up how like what situations were you put in? How many sacks should you have been expected to take if you were an average NFL quarterback at taking sacks? And then we'll count our sacks over expected. Let's reset the index because we have to do that anytime we group by. And let's sort values. Sacks, OE, and then ascending equals true. Oops. Oh, my bad. Sack. Okay, so here we go. So Tom Brady took 24 sacks in 2022. He was expected to take 49.1 sacks. So he has the best sacks over expected at -25. Jared Goff, Detroit Lions, 23 sacks he took in 2022. He's expected to take 38. And we have Mahomes, we have Trevor Lawrence, we have Dak Prescott. These are really smart veteran quarterbacks that have been able to stay relatively healthy because of their ability to avoid sacks. So this makes sense they're on top. Justin Fields on the bottom, really bad offensive line, has a tendency to take sacks. Russell Wilson has a tendency to take sacks. Daniel Jones, really bad offensive line. This makes a lot of sense as well. But are we really doing a good job of diagnosing which plays are going to end up in a sack? Let's check that with a box plot. So let's do sacks, whether or not it was a sack on the x-axis, and then the chance of a sack on the y-axis for each play. So let's see if plays that have a sack should have a higher prediction on average. We can take a look at this. So the median here, sack, when there is a sack, we have a slightly higher median than when there's not a sack. So that's good to see. That's really good to see. So that's all I had for this tutorial today. We'll be back in a couple weeks doing some continuous variable modeling. We could even get into some neural network stuff if we have time there. But I just wanted to do this modeling tutorial today to show kind of what we needed here. And so again, just to review what we had. We installed our packages, we loaded in our libraries, we we loaded in the play-by-play data set. We looked at the data set, we cleaned it, made some exploratory data analysis plots, created a feature engineered a variable, dropped the NAs, and then split up our training and test data, made a logistic regression model, random forest, XGBoost, and feature importance, predictions, and made a plot to check our model. Again, if you need this on my GitHub, it'll also be in the YouTube description. I have all the code here in case I went too fast or something. It's close to dinner time, so apologize if that happened, but we have all this code here, and then all the tutorials are on the MFans YouTube channel. So appreciate everyone watching. Thanks for all the feedback, and we will be back next time with another tutorial in a couple weeks. Thanks, everyone.